and giving me a chance to share this talk. I am going to start by saying I'm actually trying a little bit of an experiment because I have been doing data science for a long time, but it has always been sort of, it's just not a field like math where everybody knows what you're talking about when you say math, right? It is a new field, relatively speaking, and lots of people are doing it. I feel like it is unsure that everybody's thinking about and talking about the same thing when they use the word data science. And so this talk is sort of just sharing with you my perspective on it. And so I actually start all my talks with my background because it's less about you knowing me but more about understanding context of the words I use. So I think if you know somebody's background, different words mean different things. So that's why I share this. But as he said, I'm trained in a PhD in computer science and data mining. I also did a minor during that PhD where I got a master's in, macro policy and management. And then, I currently work primary appointment in public health, which what that means is I am mostly interested in answering public health questions, not developing new methodologies. But I have the skills, and so I often use data science as a tool to answer those questions, which, is dictated by that. And I run the population informatics lab, which does a lot of interdisciplinary work funded by different places. And I wanted to also talk about whose target audience this talk is to. So when I sort of put this together, I had in mind junior graduate students who've done some modeling, some programming, want to do more data science, and kind of starting out. The main learning objective for this talk is actually critical thinking about data. And so if I were to try to be more articulate about that, it's about after the 2 hours, my goal is for all of you to be able to identify and communicate the many different data decisions you will end up making when you do data science projects. You can do that by learning to think about data that you have at hand, think about what's the real problem and the gap with the data. And sometimes those data decisions you make because you're the data scientist. Other times, actually, you are figuring out what your question is to the content person. So the ability to think clearly about the data decisions, what they are. So even if you're not making the decision, for you to be able to clearly lay out to your client, this is a data issue that you need to give me an answer to. Those are really key skills that you need as a data scientist. And so that's the primary objective, with the secondary being understanding details involved with real data science. So I'm gonna try to do this by going through 3 case studies where very quickly, I won't go into the details, but to give you a flavor of all the details involved in a normal real data science project so that you can understand all of those things that are in there. And the last objective is for you to really try to leave this talk understanding some concepts of quality control in data science projects. So what I find is there's a lot of data these days. People can grab it. There's a lot of software. You can run things on it, and you've got some number coming up. So, and then people just grab it and use it. But really, actually, if you want good information out of data, there's a lot of quality control things that you have to do that often is never discussed. So these are the 3 objectives I have. And I'm sharing this slide. I teach a data science class in public health for the majors there. And this is just a direct quote from one of my students at the end. And what I did, I'm sharing this so that I think this is even a better way to articulate the learning objective. I don't know how much of this I can do in a 2-hour workshop, but this is kind of the goal of my data science class and trying to do some of that in this 2 hours. So she came to sign up for my class. You could say my class is 101 programming for non-computer science majors, because most people who are not computer science majors don't have a chance to learn programming, which is one of the key skills in data science. So I teach this class. It's 101 programming for non-computer science majors. The language I select is SAS, which is one of the most common languages used in public health. So I had a student signing up that, I'm here to learn SAS programming. And she says, she comes in with very limited SAS skills, a little bit of data science skills. She knew how to copy and paste code, didn't quite understand what was going on, but maybe make some edits to do a few things. And then she said, at some point in the semester, it finally begins to click. You begin to understand how to troubleshoot, find new ways of thinking about problems. After a while, you even feel confident in your ability to transform and analyze data sets. And I still have a lot to learn and improve, but at the end of the 15-week segment with me, and you have that light bulb come on, she felt like you had a foundation to build upon throughout the rest of your career. And that she said, you know, I learned how to think about the using of data and beginning to think like a data scientist. So I don't know how all of you might, what comes to your mind when you say, what does it mean to think like a data scientist? What does it mean to think about data? And I am not talking about statistics or modeling, which is actually a really important part. It's just that that part, there's a lot of tutorials and classes that you can learn from. What I see very little of is this other part, which is about thinking about data. So my agenda today, I'm going to give you a little background on my perspective on what data science is. It'll go very quick. And the focus is going to be on what I think is the role of the data scientist when you're doing data science. Then I will actually go over 3 case studies. There's a lot of details there, so I'm going to really go very fast over the details. And it's just to give you a flavor. But for each case study, I have a focus point where I'm going to spend time talking about it. I will try to engage you and have you think through these these issues that I've decided to talk about today. And then I'll have some closing thoughts. Okay, so on to data science. So I would think if you're here at this talk, you are agreeing with much of the school of thought that data is the new material in the new society and is on par with how much money, capital transformed our society and labor changed our society, right? People talk about those who can harness the power of data will lead the next century. There is no sector, there is no job anymore that you can do where you don't have to do something with data. Students who learn to be data scientists are in high demand. That's pretty obvious, at least for people who are here. And I'm starting with what is the official definition of not data science. I have the citation in here, but the official definition of KDD. So it's knowledge discovery and data mining. It is a subfield of databases in computer science. And the definition of it goes like this. KDD is about secondary database analysis. What that means is you get dumped data. So the first picture is, as you can see, it's a landfill. This is what I think of as big data. It's a landfill. They dump things on me. They continue to dump things on me. There's no way to organize anything in there, and that's what I have to play with. And KDD is the process of cleaning, merging, and reprocessing parts of it such that it generates human consumable, valid, novel, potentially useful, and ultimately understandable information. So that's the official definition of KDD. And to date, I believe data science is another, much more sexy word for KDD. So I like this definition of when I think of data science, I think of this is what I do. I get dumped lots of data that it's pretty much garbage as is. But I use my skills to clean, merge, reprocess them. And my goal is to get information out in a timely manner such that that information can then support knowledge and action and decisions, right? This is the basic KDD process where, again, you get data, you're cleaning and integrating them. I think most people here probably have heard of the word data wrangling. It's whatever that you have to do, but you turn that garbage dump into something that you can do. Based on that, the next step is to do feature selection and engineering, where you're actually deciding what are the measures that I need to be able to calculate so I can answer the question I have. Once you have the measures and features, then that's when you do the statistical modeling to turn that raw data measures into information. When you do that, then you actually need to look at the results that you have and validate it. Data science is a very iterative process where it's not you go through this step once. You continue to iterate until your results are valid and it answers the question that you're waiting for. And then just as important is the last step where when you have valid results, data science includes the dissemination of your results so that you can support action and decisions. But this is the general flow of data science. Here's another very popular definition of data science. I'm just using the slide from the NIST work group, where data science is at the intersection of domain science, statistical modeling, and programming skills, right? So here is one where biology is one of the most advanced fields in data science, is a research field, and bioinformatics. And so when you apply that here, the domain expertise, the domain questions that you're answering are biology. You're here to answer biology questions. The main data set that you're using, very broadly speaking, I call it the human genome data. You know, we continue to genome sequence a lot of people, so the data continues to come to that garbage dump. And lots of people in bioinformatics will then use that data, apply many, statistical modeling to answer your biology questions. Traditional biology, or any science for that matter, you need to learn the content area, biology. You also need statistics. Almost every field, you have to go learn statistics. So that's more traditional research. Though that gets pulled into data science more when you have the programming skills. And what that means is, programming skills means to me, I can tell the computer to do whatever it is I need to do. So you have to be very good friends with your computer. You have to understand your computer. You have to have the skills to tell your computer to do things. And that's the programming skill. So if you have studied your domain field and your statistical modeling, unfortunately, if you want to get into data science, there's a third thing you have to learn. You have to really learn to be able to tell your computer exactly what you need to do, right? So I work in the field of population informatics, which is something that I coined as a term, where the domain science is now social science. I study groups of people, societies, which cover fields in social sciences and public health. And so the data that I use, I call that the social genome data, which is the digital traces out there about all of us. And so that's kind of what I do for data science. This is the last perspective I want to share on data science. This is actually the next two slides are from Michael Franklin at UC Berkeley. And here, this is a perspective on data science I see less of, but I think is really important. So if you're working on a data science problem, I think it's important for you to look at 3 dimensions that are here. You should be thinking in terms of, okay, what is my timeline for when I need to get results so that I can support decisions and actions? That's one time. You should be thinking about what resources do I have to work on this problem in terms of what data do I have, what skills do I have? And those are more understandable. The last dimension here is quality. I like to talk about quality more in terms of precision. And that goes directly to when you're working on a data science project, you should always be thinking about what is the level of precision I need in my results. If you're working on a budget and you needed to get, all the spendings for last year, do you need everything to the cent? No, you just need everything to the $1,000, right? So you can go fast because you can have less precision. If you're doing an audit and you're getting audited and you're putting your data together about all your spendings last year, no, you need to tie all the numbers to the dot, right? So whenever you're working on a data science, a big data project or data science project, you should always be thinking about what is the timeline I have to do this work, what are the resources I have to do this work, and what's the level of precision that I need to meet the criteria for making the decision or decisions and actions. So that's what it is. Michael Franklin runs a lab called AMP for integrated, and AMP are initials for 3 things that he thinks is critical to data science. So I'm going to now look at the chat box if I'm going to try to engage you. Anyone tell me what they think A means? So A is an initial for one of the key elements you need when you do data science. What do you think A means? Anyone? Automate. So Eugene said automate. Not quite. That was not what Michael was thinking. Automate is an important thing. It's actually very related. Algorithms. You need algorithms. Lots of statistics modeling. Analysis. That's another good one for A. But Michael was thinking algorithms. These are similar, right? And M. What does M stand for? What do you need that starts with an M when you're doing data science? The obvious thing. You need the hardware, machines. You need machines. There's no way to do data science with your hand, right? Okay, what's the last P? Anyone? What would P be? People, perfect, that's exactly right. There is no way to do data science without people, right? So, Michael Franklin thinks if you can do data science if you have these 3 things. You have algorithms, software, machines to run them on, and people who can do things and think, right? So this is really, and these 2 slides are his slides that I'm using. I've used it for a very long time. These are not talked about as much, but I think these are one of the core things that you need to understand about data science. And these, I'm coming to the end. So now the next 2 slides is what I meant. These are 2 slides, 2 things that out there that talk about what are the skills for data science, right? So in order to do that kind of activity, what do you need? You obviously need IT and programming skills. This is about actually like telling the computer what to do because that's what you need, right? You need statistical skills. You have to understand how data can turn into information through modeling, right? You also need business skills. You have to be able to talk about pros and cons of decisions and actions. You need to be able to communicate things. So lots of Excel and PowerPoint, right? And this is really about that last piece in the pipeline where you're talking about dissemination. But most importantly, people talk about intense curiosity. The most important trait of any data scientist is intense curiosity, where you have a desire to go beyond the surface of a problem, find the question at its heart, and distill them into very clear sets of hypotheses that can be tested in the data that you have. That is something that I see throughout all things. So it's the obvious things. Yes, you have to go learn more modeling. You have to go learn more how to do computer programming. But in the worst case, you know, you can maybe find friends who you can work with or teammates who you can work with. But what doesn't work is if you are not somebody who has intense curiosity, want to dig deep, figure out what's going on, and you know, be in that garbage dump to find the answer to your question, that is probably not going to work for a happy data scientist. But if this is someone, then you might enjoy this quite a bit, right? Another one, this is coming up, they talk about technical expertise again, but here again, curiosity, right? You have to have that strong curiosity to go beneath the surface to figure out what's going on. Storytelling is another one that I like to talk about. So when you're doing data science, it's so easy to think of it as the truth because it's concrete numbers. I think of it as, and anyone who does enough, you know, data science would know that data is like anything else. Same data, same numbers can be put together to tell a different story. So it is one version of one opinion using data to tell your story, right? Cleverness, this is another one. When you're working in this world, just think about it this way. This is how I, in one sentence, talk about data science. You are given the garbage dump. You go to the landfill. Someone comes to you and says, I'll pay you money. I need a car. Can you go in there and make me a car? So what do you need to be able to go in that garbage dump and make a car? You need a lot of cleverness and to figure out what it really means. So when I say that, this is how I think about it. When someone comes to me and says, I need a car, my first question isn't to get, the first instinct is not to go in and make a car. The first thing I do is go, okay, what do you mean by a car? Yes, I know what a car normally looks like. I doubt I can make a normal car out of this landfill. So I might be able to make you a car. It depends on what you're thinking you need in the car. What's the functionality you need? Do you need 2 seats? Do you need 4 seats? Does it need to move? Is it that you need to take a picture of the car, right? So you're gonna really get to the bottom of what is it that you need. To the extent possible, it's not a one-time question. I'm done, I have a specification. You're gonna continuously be going back and forth between the landfill and this person who wants the car to figure out what they want. It is very normal for people who come to me who want information. Usually people come to me, they want information, they have the landfill. So they give me access to their landfill and go, can you go in and find me or make me X? And it is very normal for these people that my clients, that I call them, that come to me to not be able to articulate what they have in their mind when they say a car. It is usually the case they also know I'm not making them a car that they normally see that's running, right? So it's through that iteration and talking and thinking that you get to the core of what is it that you need exactly, and I think I can find it and make it for you from the landfill. That is kind of how I think of data science at the core, right? So I'm going to now move into my case studies, and before I go into the 3 longer case studies, I will spend a little time just on clustering as an icebreaker. So for those of you who don't know what clustering is, it's a very simple concept. You're in your landfill. You have a data. Somebody gives you data, and the goal here is to group the data into similar groups, whatever similar might mean. That's the goal of clustering, is to say, dump, here's the data. Can you group them into similar things? That's the goal of clustering. So here's an example. Now I'm going to take this Google link. I'm sorry. Okay, now I'm going to fumble just a little bit to give you, if you can go to the chat box, I'm going to put something in the chat box that is a link that everybody should be able to go to. Need to go everybody. So I put a Google link in the chat box. please click on the link and go to the Google link. If you go to the Google link, there are multiple links, and we're gonna, throughout the talk, have you click on these things. Each link is just a simple questionnaire that you're gonna fill out to help you participate. And then, let me see, let me get my setting back the way it needs to be, sorry. There we go. Okay, so I gave you this link in the chat box. If you click on it, you can go to the Google link. And if you go to the first one, Q0, then I have the question about related to this activity. So on the screen, you can see you have 4 data sets, right? Somebody gave me a data set that looks like this, a data set that looks like this. Yep.
We don't see your slides back on yet.
Okay, can you hear me now?
Yes.
Yeah, no, actually, my computer totally logged out and logged back into Zoom just now. But if you can hear me and you can see my screen, I can continue. So if you're at the Google link, click on the first Q0 link and answer the question. So the first data set, looks like this. The second data set looks like this. Third one looks like this, and fourth one looks like this. The question is, how many groups do you think you see in each of the data sets? I'll give everybody like a few minutes to answer the question. Okay, so I don't see any responses. Can people maybe let me know in the chat box or turn? Can you get to the link? Oh, okay. I got a few responses. I'm starting to get responses now. 2 responses. Other people? Maybe we wait for a few more responses. Okay. So yes. So yeah. So here's the first data set. How many groups do you see? Right. You don't need any specialty. You don't need any expertise to look at this data and say, I think I see X groups. Okay. Okay. So we have about 6 responses. Here it is. Everybody seems to be, well, actually not. We have more responses now. The first data set we have. Let's see. Is this coming in terms of percentages? Yes. So 8 people think 2 in the first data set. 1 person thought 3. Here's one. In the second data set, 6 people thought 2. 1 person thought 1. Another person thought 4. Right? I guess maybe I'm going to see if I can. It just depends on which one you're looking at. And then third one, actually, this one everybody agreed. Probably 3. Right? 3 groups here. This is an interesting one. The last one. This is. Oops. I'm sorry. This is a data set. There's more debate as to how many groups are in there. So I think 6 people said 1, 2 people said 2, 3 people, 1 person said 3, and 2 people said 4. So I'm going to now talk about this. Much of data science, there is no right answer. So I was hired, I was given this data, I was told to cluster. Like everybody who answered it, I have to first ask the question to the client, tell me how many groups you think you see in here, right? And I think at least in this case, it is more clear, but there are many data sets where the client thinks this is 3, but I think it's 2. And if I don't know that, then actually I'm digging down the wrong hole, right? So this is actually exactly how I feel about data science. Many of the things in data science, there are no answers. The key is asking the right questions to your client so that you can try to read their mind, right? So roughly speaking, I think there are 2 groups here, 2 groups here, 3 groups here, and I am of the thinking that this uniform distribution data set, there are no groups, so this is 1 group. It may be the case that maybe this is not the right representation of the data and there is actually clusters here, but at the minimum, represented this way, I don't see how any of these can be grouped other ways, right? So clustering is one way to do it, and then what's happening across the bar here, this is just a Wikipedia page, but it has 6 different algorithms that you apply, and you might say, well, the best clustering algorithm, for those of you who work in clustering, K-means is one of the fastest. I think that is why it's the most popular in big data clustering. But what does it really do? All of these are examples of difficult things to cluster. Typically, good algorithms, all 6 of them, will do fine if the data problem is relatively easy. This is probably the easier one, but even here, so you have more that are correct, like 3 things here, 3 things here, 3 things here. What you're seeing is these 2 things that are more closer to each other than these 2 things are getting grouped in certain clustering algorithms together, right? And then for me, when I'm doing clustering, this is the test. If I give you something that doesn't have a cluster and you're making an arbitrary answer and giving, the algorithm is giving back to me, I better know that so I need to be able to distinguish when I'm using a black box clustering algorithm, whether the answer is valid or it's an arbitrary answer because the algorithm has to give me an answer. So just think, food for thought. We got used to using Google Form and answering questions, but I'm going to continue to try to do this where the main goal is to prompt you to think about things, think about data that you see, look at data. I'm going to do, whoops. So, yes, so dbScan, yeah, the dbScan I think stands for density-based scanning, clustering. So often, and then you don't see the details here, but there's actually how long it takes. So, if I can get the same answer, in this case, dbScan gives me the right answer in my view. Mean shift also gives you the right answer, but this only takes 0.06 seconds. This takes about 100 times more. So you might think about that time element of data science. If you need to do something and you don't have a lot of time and density-based clusters are good, but they're slow, maybe you want to try mean shift and see if it works, right? So these are things to think about. That's why you are continually thinking about the 3 requirements when you're doing data science. And for the right situation, you have to pick the right thing. Okay. Let's see, moving on. So now the real case study. This one is going to be talking about measurements, and it's about liver cancer screening. So a little bit background for my case study on this one. Liver cancer is, the second leading, it's one of those cancers that actually is pretty bad in terms of death rates. One of the reasons why it is, people focus on a lot more is many of the cancers we have now done well so that the death rate is going down. HCC is one of the cancers that actually the death rate is still going up because we haven't figured it out well enough. So that is why we work on it. I mean, these are the different progressions in the liver cancer data sets. But the key thing to know here is that one of the common pathways biologically that ends up with HCC is a liver condition called cirrhosis. So that is one of the main risk factors that if you have at some point in your life, you are diagnosed with cirrhosis, then you are now on the target for when you might develop into HCC. So your chances of getting HCC all of a sudden skyrocket to be much higher when you first get diagnosed with cirrhosis. I work with a HCC specialist who's a medical doctor, and I hear him tell me all the time, if you have HCC and your prior medical records don't have cirrhosis, it's probably because it was never documented. So, this is one thing that you want to know about this field as you do it. And it'll come in, you'll understand why I think this is an important thing for you to understand in my problem. So, so why is HCC screening important? Well, typically, if you have HCC, patients typically get diagnosed at a very advanced stage because HCC as a disease tends to be asymptomatic. And so because you're getting diagnosis too late, much of the curative treatment options that are available, they are available. It's just that they're not available after a certain stage in your disease. So if you can diagnose early, then you have curative treatment. But if you miss it and then the disease has progressed to be more advanced stage, then there are no more options for curative treatments, which is why the survival rate is so low and the death rate continues to go up. Taking all of this into account, you're not surprised that, American Association of Liver Cancer, they recommend screening for HCC every 6 months using the ultrasound and or AFP, which is a stool-based test. So, knowing all of these things, experts say, you should really get screened every 6 months for HCC if you have cirrhosis, because once you're diagnosed with cirrhosis, your chances of getting HCC is much higher. If we screen you every 6 months, because they don't have symptoms, we might be able to catch you early enough so that then we can look at the curative treatment options, right? That is the things that everybody understands, but all the literature that has been done so far basically says Well, too bad. That's not what's happening in reality. Only 20% of patients with cirrhosis actually receive HCC screening on a regular basis. So this is why I continue to work on this research problem to say, what can we do to improve screening so that we can improve survival of HCC patients, right? The overall objective, I have 3 aims in my project. The first aim is to design and test improved alternative approaches to measuring HCC screening in administrative data. So I say administrative data, that's that landfill. So what I know how to do, I'm not a medical doctor, but what I do know how to do is find information out of dumps of data from the hospital, claims data in this case, right? So we have that data. First thing, if you're gonna do anything, you gotta be able to measure it. So my first objective was to say, what are ways I can detect when screening occurs in this landfill of like dumps of data? And we worked together to actually, first of all, figure out what's out there. It didn't work so well, so we're trying to improve it. The second aim of the study is, taking using the newer, better measures of HCC screening, can I run some regression statistical modeling to figure out what patient and provider factors impact screening so that we can figure out, are there things we can do to change in the provider or patient factors that would improve screening? And then the third aim was to say, using those new measures of HCC screening, can we confirm the early tumor detection rate as well as overall survival and the relationship between the screening and overall survival. So these were the 3 big aims of our study. I won't be going through all of these in my case study. I'll just be probably focusing mostly on that first one because that's about measurement. So here we are, we have the 3 aims. Each of the 3 columns represents the 3 questions. We identify the data source. In this case, it's your Medicare, and we have 2 data sources, the American Medical Association master file. I'll talk about these a little bit more later. The years that we decided to do this on is from 23 to 2013. So we have about 10 years of data. That's sufficient data to talk about this reasonably confidently. The main dependent variables when we're modeling, for the measurement one, it's a descriptive study. So there isn't a dependent variable because we're not doing modeling. We're just doing a descriptive analysis. For the second and third aim, we are doing modeling. So the main descriptive dependent variable for the looking at the impact of patient and provider factors for screening is, what you see here, the PUDF for HCC screening. The proportion of time up to date HCC screening is a measure that we developed in the aim 1, right? So we're going to develop in aim 1. We're going to use that to model in aim 2 to study, factors of patients and providers that impact screening. And then we will again use that model to look at survival rates and early tumor detection. So the main variable in the looking at survival is early tumor detection. And that is, Milan criteria is another measure that is commonly used to say you've detected the tumor early enough so that you can go for surgical procedures, which would then give you a better chance of survival, right? So that's what we're doing. The main methodologies, the first one, again, is descriptive. The second one was a 2-part toolbit model where we say, what are the chances of getting screening because screening rates are so low? And if you are getting screening, how much? So that's a 2-part model. In the third one, we're doing a logistic regression as well as Cox proportional hazard models to look at survival. I will, again, be not talking a lot about 2 or 3, but this is how I'm just giving you a big, the general feel of the full study. And then when we look at the final sample, our final main sample are all HCC patients, which was about 14,000. We also have a subsample of those who actually have known cirrhosis, and you can see how small it gets. Now my sample size is only about 3,000, right? And then we did have to do some more adjustments for the third aim because that has to do with survival and death. So we had to exclude people who died before the start of the data. So of the main sample, we excluded people, and then so both samples get a slightly smaller. But this is the basic summary of how I think of this as a data science project. So a little bit about the data set. A SEER Medicare is the data set. So SEER is the cancer registry data. What we mean by that is disease registry data are things where some person, like a nurse, fills out you can think of it as a paper form. They will look at medical records, review medical records, and fill out a form that you are, as a hospital, required to do so that we can keep surveillance of cancer in the US, right? So you have hospitals and staff who look at patient medical records to fill out, you can see why you can't fill out a lot of things, but you have to fill out a few things that has been pre-agreed to, and it's a standardized form that people have to fill out. all of that data funnel into the cancer registry that gets collected. And SEER is a cancer registry. So here's another thing. I would like to say SEER is a national cancer registry for the US, but that's not true. It has 15-ish states. So in the map, you see the dark colored states are there. For us, Texas is not there. Texas has a cancer registry. It runs its own cancer registry. It cannot submit to SEER because it doesn't follow all the standards of SEER. So SEER is the biggest kind of national list, cancer registry data that's available. And then the SEER-Medicare part, Medicare is the big data part. Medicare is the claims data. So you can think of this as, all the bills that were paid on medical services by one insurance. That's the Medicare is the insurance for older people in the US. So Medicare is the Medicare data. So the SEER cancer registry data get record linked row by row to the Medicare claims data, which is all the payments that the federal government made for older people in the US who get healthcare, right? So that's the main data source. We chose to use that because that is one that has the most representative. It does not represent all of the US. It does not even represent, all the age groups. Medicare is insurance primarily for people 65 and older. So for example, if I was studying child cancer, this wouldn't work. Medicare doesn't fund much of child health insurance, right? So in this case, HCC is a disease that often occurs in older people. So although there are people that are younger than 65, not in our data set, Medicare can cover a good number of them, so we will do that. So, things to look at are things like here, where we can see that amongst the 15-ish states that we have, population-based cancer registries, it covers about 34.6% of the US, right? So what I'm doing is having you start to think about, of the many things available to me, what is the thing that is most usable? Well, this is what I could locate. Is it a nationally represented something? No. Is it even 50%? No. Is it still useful? We think so, right? So this is what we identified, but if we're going to use it, it starts to be, you want to document what is it really that you have. So, I have a cancer registry data set that represents about 35% of the US cancers. I also have claims data, all the health services payments made by Medicare for people who are 65 and older. So that's the data set that we came to use. And then you think I'm done talking about data. No, I'm not, because once I figured out what data to use, then the actual real inclusion exclusion criteria that you have to carefully work out, you're working with in my case, I'm working with a clinical researcher. I have to sit very carefully and look at it to say what is possible. So I'm gonna, without going into too much detail, for example, inclusion criteria. Of all Medicare beneficiaries who have been diagnosed and confirmed for HCC using a ICD code, this is a data field that's in the claims data. You have to go look and you say, if anything says ICD 8170, that's the confirmed HCC diagnosis, right? So we're looking for, in the claims data side, everyone diagnosed with, in that field sitting 8170 from 2003 and 2013, right? There are other things I'm bringing in. In addition, actually in this case, because I have the cancer registry data, those are human filled out. They tend to be cleaner data than claims data. So on the cancer registry data, there is a field diagnosis for HCC and a date. So when you have two sources of when was this person diagnosed with HCC, you do have to think through which is the one you're going to use when there's a discrepancy. So in this case, in conversations and understanding of the data source, the right data source to use was the cancer registry. So we did inclusion criteria based on the cancer registry side of confirmed diagnosis dates. So we said, everybody with confirmed diagnosis on the SEER side from 03 to 13. Among those people, we have lots of exclusion criteria. So, here's the list. I'm going to just say, here's one. We said, it's very important that I have tumor characteristics. This is about, in the cancer registry side, there's a few fields that talk about how big the cancer is, where it is, and things like that. If key fields are missing, then we're going to not be able to use it, so we drop it, right? Patients who only saw emergency providers, right? That means these people are not in the main claims data set. So, patients who only saw providers one month prior to diagnosis. So there are all these conditions that you have to get correct. This is what I meant by, I spend much more time talking to my clients than I spend in the landfill working with data and algorithms. especially in the beginning. So you work out all the details to say exactly, if I want to answer my question, what are the things I need? So this is now a detailed data flow that I often do in all my projects that says, you know, you might look, I start with 55,000 patients in my data set. When I first started, this is when I said everyone who has HCC cancer between 03 and 13, they give me 55,000 patients. Well, that's not exactly it, because then I go through all my inclusion and exclusion criteria, you know, about patients having been enrolled in Medicare. They can't be on the management side. They have to be on fee-for-service. They have to be there for at least 3 years. All of these conditions, I have to now start dropping people very quickly. And then my final cohort is ending up at that 14,000. So you see how much you're quickly dropping data. You have to do this, because if you work with this, you're still in the garbage dump. You can't answer your question, right? So having a very clear thinking process where you know what you started with, why you're dropping things and how you're dropping things, very, very clearly, very, very detailed, and where you are to say, this is the thing I can now use to answer my question. Right? And in our case, we had we had three, right? We had here's the primary one. Then we said, of these people, there are people that have cirrhosis, right? So then we identified there's a small group. So we will do some analysis with the cirrhosis cohort, which is a much smaller cohort, as well as among the main cohort, you know, we are dropping people because 175 people died before the study period that we were doing. So then, you know, you have a smaller. So, you know, final survival for the death goes from 13,714 to 12,609. Final cirrhosis for death study goes from 7,972 to 7,97. So I would say if you're working on a data science project, when you're done, you should be able to draw this. You should draw it. Sometimes when you're writing papers, I find there's not room, this gets dropped. Even if it does, for my internal lab notes, I need it. So I can't emphasize how important it is. When you start to do this, this isn't something you do at the end. This is something you start to do in the beginning. This continues to change and iterate. As you work on this diagram, it is really helpful for you to be able to think through data and the details that you need, and documenting the details that you need when you're all done to write your paper, right? So we did all of that, and then here's the general descriptive of the final sample that says, you know, the average age of HCC patients diagnosed during the 10 years is about 70 across, you know, I'll talk about this a little later. This is the screening, right? So the first column is consistently screened. That's a good thing. Second column is inconsistently screened, which means not so great, but still screened. And then, of course, the third is no screening, right? And the definitions for these three things is the first aim. But in this case, we're using what's in the literature where, you know, consistent screening means 1 abdominal ultrasound per calendar year. If you remember, the recommendation is screening every 6 months. We don't even do that because already you can see of our sample how small the consistent screening is. If we were to use 6 months, because that's what we should do, this number would get so small that actually the modeling won't work. So, you know, you can see the biggest group, no screening at all. This is 3 years prior to diagnosis, right? So most people have no screening. The next biggest group has inconsistent screening, which is at least 1, but less than, you know, per year. And then consistent screening is what we're looking for, which is every year, which is still smaller than the recommended once every 6 months, right? So, and then we had variables like, you know, age, sex, all the demographic things, the year of diagnosis, the different clinical conditions, and we continue. So this is the general setup of things. So what do we mean by, what do we do for the measurement of HCC screening? This is the first thing I want to talk about. So we looked at the literature. I just explained how in the literature, the only things that are available for measuring HCC screening is either using a categorical variable of 3 categories: no screening, consistent screening, and inconsistent screening. We found that this was sort of out of date. It doesn't click very well with the 6-month recommendation. So our goal was to say, can we do any better in measuring this in the claims data that we had? So method 1 is what I talked about. That's in the literature. Method 2 is what we came to. It's called proportion of time up to date screening. It's a measure that is, this kind of approach is common in pharmacy literature. So kind of we adapted it. And here's how this works. So over here, again, I'm reminding everybody, this is looking for that screening every in the 3 years prior to diagnosis. In this case, the 3 years turns into now 36 months. So you are potentially getting screened, you know, 36 months. Because the recommendation is once every 6 months, we gave it a leeway of 1 month. And we said, if you got a screening then you are good for the next 7 months. And you are due another screening in the 8th month. So that's the concept here. So how we calculate this is, say, if you have a patient who received an ultrasound in January and another one in July, then you get credit for 7 months in January, 7 months in July. So in total, if these were the only screenings you had, you would get your proportional time up to date screening would be 14 months out of 36 months, which turns out to be 38%. So this measure is unlike the other one, which is a categorical measure, this is a continuous measure that goes from 0 to 100%, right? So that's how you do it. What happens if patients are getting a screening closer together? So here's an example where you get one in January and one in March, then there's an overlap of that 7-month period. So then, although this person had 2 screenings as well as the other one, because those overlap, you only get 9 months out of 36 months, and that would be 25%. So this is a new definition of measuring HCC screening, and we wanted to see how well this can detect the signals to do these other aims that we had in the proposal, right? I'm moving on to a totally new topic now. And this is what I meant by real world problems in the data problem. So this topic is totally new in that it's not like every single abdominal ultrasound, which is what is done for HCC screening, is done for HCC screening. Many people get abdominal ultrasound. It has nothing to do with HCC screening. So we have a data set. We can identify when the abdominal ultrasound happened. We know that some of those were done for HCC screening, and we also know that some of those were not. We have no way to distinguish which one of these were actual HCC screening. So what happens at the moment, we just ignore that fact. There's nothing we can do about it. We'll just ignore it. So all that consistent, inconsistent, measuring proportions, it's all based on the assumption, the incorrect assumption that everybody knows that all the ultrasounds were done for HCC screening. That might sound pretty awful, but one thing to consider is if you were actually, these are all patients who were diagnosed with HCC some point soon. So the chances of the ultrasound for these populations being an HCC screening is higher than the general population. So keep that in mind. But because of this, which one of these are actually HCC screening, there was somebody, Dr. Richardson, who did some modeling to say, I'm going to try to build some probabilistic model that said that ultrasound is more likely to be HCC screening, whereas this ultrasound is less. So he used a big data set. He did some logistic modeling where at the end of the day, you have things like abdominal pain, ascites, drug dependency, HIV, HFE. So he built a logistic model that said, if you have a claims data set and you have a row that says, here's your abdominal ultrasound, and you get all these other variables, then you can put that data in here. You will come up with a number that says that's the probability that we think is related to HCC screening intent, right? So that's number one. Once you do that probability modeling and it comes out, you actually need a threshold, because all this does is gives you a number. This is the probability of, right? And so if you need to know, is this an actual HCC screening or not, so that I can count, does it count for being consistent screening or not, then you have to have a threshold. So this is another common thing in data science. Whatever you're doing, you finish your modeling, it gives you a probability. You're looking for, okay, so now what is an appropriate threshold? So they did some studies with the results of the data that they had in hand, where they were actually, they had clinicians look at the actual medical records behind these things and said, here's the pile of things clinicians defined, looking at all the medical notes. These were actually HCC screening with intent. Here are the ones that are not. They did the modeling. They looked at where the cutoff should be, and they said, oh, the cutoff is 0.38. So what I'm trying to say is, so I'm doing this. We would like to take into account the intent of screening, because that would make our model more accurate. And we looked at the literature. We found something like this. We applied this to our data. We wondered about the threshold, wondered how applicable this threshold from that data set is to our data set, but we didn't have other choices. So we used the same threshold. And then, we applied it. So then now we have not only have the count of, when the screenings occurred, we also have a probability of taking into account the intent of screening. So this is how I end up with 8 sets of analysis. So again, first of all, there's 2 methodologies. One using the categorical variable broken out into 3 categories. The other one is using the continuous measure, where you're looking at a proportion of the 36 months that were covered. right? Within each, you can use the measure that says it's with intent, and or you're going to ignore intent and say, I count everything as being intent, right? So that's how I did it. We then did this on the full sample as well as the subsample. So this is how I ended up with 8 sets of results to look at to figure out what's going on in terms of measuring intent, HCC screening, right? So what do we find? So answer to the first question, what do we find? These are descriptive stuff. Most importantly, so here, okay, let's look at this. So the top 3 is primary sample results. The bottom 3 are cirrhosis sample results. We have 10 years of data. We cut it up into 3-year periods so that we can see trends in time, right? The longest light bar at the top is no screening. So, earlier years, pretty much no screening in the primates, like lots of no screening, a little bit of improvement over time, but not by much, right? This is the primary sample, so it's not people who are, so is this any better if you actually diagnose with cirrhosis? This is a smaller cirrhosis sample, and you can see that yes, at least for the cirrhosis sample, they are getting screened much more, right? So no screening rates at the full population is about 50%. No screening rate at the cirrhosis sample is only about 30%, right? And the improvement rate, 30, 27, 25 feels a slightly better than, almost no statistical change in rates, right? So people who have been diagnosed with cirrhosis are getting screened more, and the rate of screening increase over time is more. So you can see that, right? So in the cirrhosis sample, right? Proportion of patients receiving consistent screening steadily is increasing over time, right? So what I'm trying to say is we did all of those analysis. There are lots of questions, even with the measure, whether this is okay or not, but you can still see trends that you can sort of hang your hat on, right? And this is where we're using the old way of doing, consistent, inconsistent, no screening. We're ignoring the 6-month recommendation. What does this look like with the new measure? This is what it looks like. So now this one says, okay, so this one is all patients without screening intent. That's everyone. This is where all patients with screening intent. That's why when you look across these two, numbers get smaller, because things that were considered screening in this, when I ignore intent, are all of a sudden, I'm including the intent, so then I'm dropping a lot more. So to understand this graph, the largest bar here is everyone that never got screened, right? So everyone that never got screened, remember the previous slide that said about 50%, that's about 50%, or higher than that, a little bit higher than that, right? As soon as we say, let's take into account the intent of screening, and you're gonna drop some of those screenings that were abdominal ultrasound that we don't think was intended for HCC screening, then of course no screening goes up, right? But you can still see the same trend, right? So that's what you're seeing, and then you have hikes. This is the full sample, this is the known cirrhosis sample, right? So again, here's where this is the without screening intent, this is with screening intent, so you're dropping those things that you thought were screening that are not, but the general trend is, so the idea is no matter how I turn it around, the general trend is there. And you're really looking for that general trend to see that's the information I am trying to extract to tell my clinicians, right? So regardless of how you measure it, whether with intent, without intent, categorically, numerically, continuous variable, you find that screening rates are still quite low, right? That's the most important. So what we say is we have now strong evidence to say screening rates are still low. We still need to invest a lot of effort to increase the screening rate in general. The good news is at least we are steadily increasing over time, right? And that's kind of what we learned from this exercise. So you can see, this seems like such simple thing that, maybe it takes a day, like you have the data, go grab the rows, count the things, count the percentage, you're done. But you can see in all of the things I took time to talk about, there's a lot more if you want concrete numbers that are good with quality control, right? So the main takeaway here is the gap between real world and data world. So here's a question. In the real world, I would like to measure level of screening so that as a clinician, I can go to people, policymakers, and say, we need to work on improving screening. I would like to measure it so that it is accurate enough so that I can understand that these are actually screening with real intent for HCC screening, right? And I would like to measure it for patients who have cirrhosis, since the recommendation is about people with cirrhosis, right? So in my real world, what I want to do are all the 3 things I listed here. If you look at what I described, I am pretty much not able to do all of those in any full satisfactory way. So for example, the reason we aren't really using the cirrhosis sample as the only sample, it's too small. I can't do a lot of the things that I need to do with only 2,500 people, right? I need to take advantage of the 1,300 people available that don't have cirrhosis. So although that's why we always do the cirrhosis analysis, but it's a small sample, so we're checking again with the large sample, right? Again, this is kind of similar with the intent variable, right? It would be great if I could drop all those ultrasounds that look like it's not intent, but that one actually has other issues as well. So yes, I want it, I really want it, but is the modeling of the logistic regression that I was using and the threshold really giving you what you need, and is it accurate, right? It's one attempt. I actually don't have a good lot of, let's say, confidence that that model is actually grabbing intent well. So, you know, so the question to ask as a data scientist, so you looked at the literature, you tried it. You really have to ask the question, is this worth doing? Is this adding value to my analysis? Or is it just more complicated because I have, you know, twice as more to do? When I added, I'm losing the data because I have to like delete all the screening that looked like it wasn't intent, when the modeling itself might not be very accurate. Or even if the modeling was, the threshold isn't good, right? So you have to ask the question, do I really want to use that intent algorithm that I found? And, you know, that's something to think about. I'm gonna just, now look at the chat box again. Of the people that are here, if it were you doing this, would you apply the logistic model to go through the screening to say this is with intent or not? Or would you say, you know what, that's not quite helping me and it's just making things more complicated, so I would drop it. So I want to see if, you know, yes or no. Would you think it's good to use that intent modeling and that it will improve it, or do you feel like it's just adding complexity? Is that too difficult of a question? Yes. Okay, so we have 2 yeses for using the intent model. Anyone else? Is there anyone with a no, we shouldn't use the intent model? So we have a third person that's also in the yes box. Is there anyone here who thinks, you know what, we should not use that intent model? No one. This is very interesting to me, because honestly, I would probably not. I think actually the right answer, for me anyway, the right answer is I would do sensitivity analysis. That's actually how I presented it. So it's not that I wouldn't do it, it's that I would do it to confirm that it doesn't add too much more value. And then when I say I wouldn't use it, I mean in the executive summary, when I'm presenting my results in a succinct way, I would probably not present the model that has the intent in it. I would present the other model because it has more data on it. So much of data science like that is, to me, I will do more things, but then you have to boil it down to the essence. And when I boil it down to the essence, I'm often dropping things like this that bring in complexity, right? So that's the real world. The data world actually has all of these problems that I was telling you about, right? And then not enough events of interest to model. So both of these are things that you have to consider when you're doing this. Often, like in my world, it's not like if I wanted to do something that the data exists. Either the data doesn't exist or the event doesn't exist, right? We talked, when we were doing this, one of the things that came up very often, you know, the recommended screening is every 6 months. So you would like to have something, just count, you know, how difficult is it to count? Does the event occur every 6 months? The problem and the reason we couldn't do that is if you do this, because so many people weren't getting screening, there was nothing left to do the aim 2 and 3. And so we couldn't do that, right? So these are things to think about. The rest of this is gonna go really quick. So I wanna give you a flavor. So all of this for what? Just so that I can do aim 2 and 3, right? So aim 2 is looking at impact factors for patients and providers. We did a univariate analysis and multivariate logistics. Actually, I wanted to go to aim 3 because this is it. So here is where we did the actual survival analysis. In this case, we ended up using what's in the literature about no screening, inconsistent screening, and consistent screening. Using those measures, this is the survival curve. So for those of you who haven't learned how to read a survival curve, the way this goes, at the beginning of the time period, you have everyone who is alive. As time goes by, some people are dying, and this line represents the people dying. and we are at the 60-month mark, so this is a 5-year survival curve, right? So at the beginning, everybody's alive. 5 years into it, only about 20% people are alive, right? The thing is, you have 3 lines here. Blue line on top is the consistently screened group. The red line is the inconsistent group, and the green line is the not screened group. So we can say, and I believe doing all the statistical modeling, we can say we are statistically significant to say that if you were somebody who was getting consistent screening before you got diagnosis, your survival is much better statistically than those people who don't get screening. And you are seeing that screening is worth doing, right? And now, if you talk to health economists more about the causality, so this is only association. That's another important thing. This is only association. What we can say is for patients who are getting screened prior to diagnosis, then your perspective of surviving your disease is much better. So you should do so. That is just association. This is not saying because you got screening, you are doing better, right? There can be many reasons why you are doing better that may be associated with the screening, right? For example, it could be the case that actually you had, you were screened, and thus that was the logic we were saying. You were screened, and thus you were found earlier, and thus you got curative treatment, and thus you did better. So if you had to talk about causality, is it the surgery that made you do better? Is it the screening that made you do better, right? So this is all about association, but it's important to be able to somewhat reasonably measure screening so you can do studies like this that then say, okay, this is why we need to go and still work on, improving screening. Does that make sense for everybody? I think this is the end of my case study. Yes. So this is just to say, I had 3 real questions to start with. Here is the answer to the 3 questions. Number 1, we found that HCC screening was underused for patients with cirrhosis throughout, even though it did get better over time. Number 2, screening did contribute to detection of liver tumors at later screening did contribute to detecting liver cancers at earlier stage, and so if you didn't do screening, all the people who didn't get screening, then your liver tumor detection was later, which then ended up in shorter time of survival. And however, the proportion of patients screened for HCC has increased over time, right? So we did this study. We did all the question 2, question 3 modeling using both measures. And we tried to see if one of the main goals was to say, can we better incorporate the 6-month recommendation in the real world into the screening measure, right? If you were doing that categorical one and you just said, we will now take consistent screening to mean every 6 months, that number that was 900 is going to get even smaller. And then those numbers were so small that you couldn't model. So we were able to model using the proportional when you use the 6 months, right? So that's a way to reflect in the measure reality better. But at the end of the day, when you saw what we did with the survival curve, right? So if you look at this, the categorical nature of the old measure makes it easier to do the survival analysis. The continuous variable, it wouldn't come out like this, and it would be more complicated to look at. So this is about presentation that we did this on. I think that is the end of my case study. Any questions? At this point, I think we should have a short break. Should I start? Okay,
yes,
so
please.
Yeah, so this is a new case study, and this is something totally different. So we're not going to talk about liver cancer. It's called Medicaid waiver evaluation. And the problem I'm working on here is actually something that I'm sure all fields do all the time. You're trying to detect if there was a change or not, right? So, oops, I'm sorry. That's the control. So a little bit of background so you can understand the things I'm talking about. So this is now about Medicaid, not Medicare. Medicare is insurance for older people in the US. Medicaid is insurance for poor people in the US. So Medicaid 1115 waiver is something where Medicaid is insurance for poor people in the US. It is one, unlike Medicare, where the state has a lot of say. So Medicaid programs are different from state to state, but the federal government still funds a lot of it. So there's a lot of negotiations that may happen under the Medicaid program between the state agency and the federal agency. So in this case, Texas got what they call an 1115 waiver that involves spending billions of dollars. based on a negotiation between the federal government. The federal government agency is CMS, and Texas state, with the agency is Health and Human Services Commission in Texas, right? So the two agencies negotiated how to spend billions of dollars for better population health in Texas. And they do a lot of things in it. One of the things is called DSRIP, which stands for Delivery System Reform Incentive Payment Program. So what this is, the project, the bigger project is I was hired to do an evaluation of the whole 1115 waiver in Texas. So Texas got 5-year waiver, they finished it, then they got a renewal, and they're now in the renewal second phase. I was a part of the evaluation team in the first evaluation. I'm now the lead of the second evaluation. But the thing that I'm going to talk about today is just the DSRIP part of it. And the question is really, it's pretty simple. What was the impact of the DSRIP program and all the investments we made, right? So just a little bit more, just like you had to understand cirrhosis, the thing that you have to understand about DSRIP is, this is how DSRIP works, right? So they take Texas, they divide it into 20 regions called Regional Healthcare Partnerships. We call it RHP. And the question was, you know, we spent all these money to improve population health. One of the theoretical ideas is we would like healthcare providers in the region collaborating and working together to keep the population in that region healthy. That seems like a pretty, you know, simple, right thing to do. So, you know, the program started in 2013, it's still ongoing. So now we're at 2020, about 7 years, billions of dollars already spent. And the question that CMS and the state wanted me to try to answer is, did DSRIP change collaborations over time? Did collaborations increase? Seems like a pretty simple thing, kind of, if you can measure collaboration. So again, we're going to start with, well, how would we measure collaboration so I can quantify what happened over time, right? This might be an obvious thing to some of you, but it's pretty, one good way to do this is by using graphs, right? In the graph here, you see nodes. Those are the providers in one RHP. So, you know, different shapes and colors represent different types of providers, like hospitals. You know, pink is hospital, right? Versus, you know, that you have county governments, health science centers, health departments, and different shapes represent different types of providers. So you have nodes that represent the providers in the RHP. The edges, the lines connecting the nodes, are the collaborations that you are having, right? So if organization A is collaborating with organization B, you would have an edge. And then now you have a concrete way to measure collaboration for a given RHP. And this is just an example. So if I measured the collaboration at time point t0, this is an example where I measured one. This RHP, I guess in this case, has 1, 2, 3, 4, 5, 6, 7, 8 providers, right? They are all kind of working in certain ways to each other. This is what it looks like at t0. We measure it again at t1, and you know, there's more collaborations going on, so the edges increase. Sounds pretty simple. Like, there's no big data, there's no data science here. And I would say, I thought so too. I'm gonna start by saying this is one of the most difficult problems I've worked on in the different things I've done, even though these are Excel sheets. So I think I'm gonna try to work through with you what the thinking is and where I'm running into problems. This is actually literally something I'm working on right now. So this is why I grabbed it, because it's fresh in my mind. So, I mean, on the setup, it's pretty simple. Like, get an Excel sheet, make a graph, count some edges, you're done, kind of. So let's see what the issues are, right? So here's the basic method. As I said, that using the graph in social sciences, the methodology is called social network analysis. There are software for social scientists who don't code as well as we do, some of the engineers. So if you're not a fancy programmer, you can get specialized software that can do graph algorithms reasonably well, and they're often called social network analysis. In a more quantitative field, you know, graph algorithms, we all know how to count nodes and edges and things like that, right? At the end of the day, what you're doing, the measures that you're looking at, the number of edges, the type of edges. So in our case, in this case, you know, we care, is there any collaborations around sharing data? Is there any collaborations around sharing resources? Like, for example, are you using the same building, right? Or, you know, are you collaborating by having joint service delivery? Meaning, you know, we're providing a service, we're gonna collaborate together to provide that service, or do you not care? It doesn't matter what kind of collaboration. Do you have any collaboration with, right? So you can think about types of ties. That would come into the weight on the edge if you're doing graph algorithms. So you could say, you know, I have a collaboration with B, And the 3 types of ties would give you a weight of 3 on the edge versus, I'm not collaborating with A as much. There's only 1 type of tie. So you can now start to talk about nodes, edges, and weights on edges. And you can also measure things like density of network and centrality of network. Like, is this a network of mostly everybody connected to one person, or are we all kind of a network, interconnected? So, these are very common things that you can do just to get a feel for what the data is behind it. So I'm going to just say, first of all, I'll say it's survey data. I will say, to me, it's data science in that I didn't collect the survey data. So again, I would dump the survey data. And we'll talk about what the dump was. But for the time being, let's see what they collected. So they did a survey data, like simple like this. So this is an example of one of the smallest RHPs in Texas, which only has 4 providers, right? So you just ask each of them, do you work with organization, the other 3, right? Do you collaborate with organization 1, 2, 3 for service delivery? Do you collaborate with them? Do you share tangible resources with them? You have data sharing agreements with them, and you answer yes, not sure, no. So you collect data. This is the form of the data that we got collected. And because this is pretty complicated, I realized actually the case studies are taking longer, even if I'm not going into almost no detail. I'm going to focus on just density of network for this conversation. So here we are. What's the density of network definition? Pretty straightforward. Proportion of ties that exist among ties that are possible. So if all organizations are collaborating with everybody else, the density of the network would be 100%. If nobody's talking to anybody, then it's 0%. Usually it's something in the middle. Very straightforward. So we move on. Okay. So this is one form of data I was dumped. So I was actually given the raw data of the survey that was collected like this. And then along with that, I was given the report that they wrote. Whoever collected the data, there was a report that was written, and I was given the report. What you're looking at is what was in the report. And I can see, we have 20 RHPs. We see the density of each RHP at each time point. They had 3 time points, one pre-waiver, one 2013, one at 2015. And then in their report, they changed, they looked at time changes from T0 to T1, T1 to T2, and T0 to T2, right? So this is not what I did. This is the start of what I got. And here I am now asked to say, go measure some more things at T3 in 2020, as well as this is a 5-year project. So they wanted us to actually measure like time point T3, T4, T5. So it is true. I am also now collecting new survey data, but I'm also trying to make sense of and using the data that I was given, right? So that's what I got. And, the first thing I'm doing that I would say is really actually comes up a lot in data science. I do a lot of replication studies. That includes replicating my own work. So the first thing I had to do when I started this task was I had to say, given the raw data you gave me, can I replicate this table? Because if I can't replicate the table, I don't know what's going on, right? So the first thing I did was to say, okay, I got some raw data. I got my staff to say, go look at stuff, learn things, please replicate this table. Because I thought it was really easy. So I said, go. And it wasn't happening because they couldn't replicate it. And then we had to figure out what was going on. So that's number one. And then the second thing was, let's assume I was able to replicate the data. Then the second task is to write a new report with new collected data that would add to, right? And then as I'm doing this, I have to think, first of all, whatever methodologies and this data, all the data decisions, remember, if you think of the first case study, there are a lot of data decisions to be made, and each decision needs to be well thought out. So there's a lot of that here too. So they did that. That gets summarized into these results. So the reason I do replication studies is because if I do the replication studies, I can find all the data, critical data decisions, and I can make sure that even though it's not fully documented, that I know what they were. That's kind of what the replication is. So once I do the replication study and can find all the data decision points and then know what they did to get to those results, that now opens up a new set of questions that say, that was a data decision. That is the decision they made. Is that the best decision? And do I keep it or do I change it? And if I change it, why? Right? So that second task is kind of important. As I do this, this is now about me going into you can call it a data science project or not, but there is a data analysis decisions that were made. I'm trying to go into it with very little documentation as to what happened in the first waiver evaluation to say, I can now backtrack and find all the data, critical data decisions, and then look at the ways it was done. So that's kind of my general goal here. So here's where I'm going to start. Now, first of all, this is again another RHP, this time with 8 providers, right? So I'm just reminding you, this might look small. There are 20 of these. There are 3 time points. This isn't even me. This is the data I got. There are 3 time points. There's now 60 of these. And each RHP goes from, n providers, n nodes to 38 nodes, right? But I'm going to use an example. And this is another thing I want to say. When I work on big data projects, and I mean big, like 20,000, 100,000, 100 million, how you figure out big data is to look at small data. The key thing is to know where to look and find the small data that has the complexities that you need to deal with, but something that you can put your hand on. So that is something that I keep repeating to all of my students. Don't think big data is something that you just, run algorithms on, run models on, and send commands to. If you don't look at your data, you don't know where the complexities are. So one of the things that I do a lot in my projects is I go, where can I make a small thing that I can play with and look at and see what the dynamics of the data is? But still, it contains the right amount of complexity in the real thing. Like, is it representative enough? So in this case, I could have picked an RHP that was 38. That would have been impossible to look at, even if it wasn't a presentation. So I chose one that is not 4, but we chose one that is 8, in the smallest side, but not the smallest thing. So this is the raw data that this is one of the 60 raw data I was given. Literally, I was given 60 Excel sheets that look like this, right? So here's what I got, and how do you read this? So the first thing is, first of all, I see, you're gonna go across and you say, okay, Webb County participated in my survey. And what did they say? They said they collaborated with Boulder Regional, City of Laredo, UTH San Antonio, Driscoll Children's Hospital, and Laredo Medical Center. They did not collaborate with, Maverick, Camino Real, and South, right? This is South. So you kind of read things like that. I'm like, okay, I get that. I can understand this. So then I'm moving on. And I want to actually just take a little time to say this part of the talk is really about data wrangling. I'm sure everybody here has read this article. This is a very famous article in data science. And all I wanted to point out to you is lots of data science can be fancy modeling. Much more of it, 30 to 80% of working with big data is actually janitorial work, which is about cleaning data and figuring out how to turn it into shape so that you can do this. And this is really what this part of the talk is about. So here I am, same thing. First thing I do, I say, you know what? This diagonal is self, so I don't need an answer there. So first thing I did was I X'd out the diagonal because I'm not looking for an answer. Easy steps. This is just helping me think through this. The next thing I do, I say, hey, look, Webb County said, yes, I work with City of Laredo. And then I asked City of Laredo and they said, yeah, I work with Webb County. Great, they both work with each other. Nice to see, right? Is this what's happening in the data for everyone? No, right? So here's one where I see that Laredo Medical Center probably did not participate in the survey. There is no answer at all for anything. So this is where, this is a survey. You ask everybody to do it, not everybody does it. So first thing I say is, I see, in this case of 8, 2 people, so I think both Driscoll Children's and Laredo Medical Center did not participate in the survey. Oh, actually there's one here, so maybe they did. That is unclear whether they did or not, right? And I don't have documentation telling me otherwise. So that's one. But then I'm thinking, okay, I have missing data here, so what do I do? Well, I can kind of do this, so this slide is to try to demonstrate. So although on the original data I got, I think it's this original data I got, over here there's nothing, and over here there's nothing. This means something totally different because up here it's actually 0, meaning Webb County did the survey and they said, no, I don't work with Camino, and no, I don't work with Maverick. Whereas down here for Laredo Medical Center, there's nothing here, but this isn't, they said, no, this is, I didn't bother answering the question. So you have to distinguish between missing data and actually negatives in data. This is another common thing that when students start to work with, they forget this part. So sometimes data come very clearly labeled, many times they don't. It's your job to think through the data and figure out which one is which when you can. And at least if you can't, know that you can't and have to deal with it, right? So first thing I did was to try to distinguish those things. And then for those missing, I said, well, maybe I can impute it, because although I don't know what Laredo thinks about collaborations with everybody else, I have answers from 6 other people that tell me they did or did not work with Laredo. So hey, maybe I can use that information to impute it and guess what Laredo is, right? So that's one way to deal with missing. So I can take the answers from other people and impute it into this space, right? And then I have the other problem here where we say here, so Webb County said, yes, I work with Boulder Regional. Boulder Regional, who did do the survey, said, no, I don't work with Webb County. So now I have one where there's actually, you might think, contradictory information. And you're working, okay, so now what do I do with this? Okay, so at this point, I would like people to go back to the Google Docs and go to the Q1 link, right? So I just kind of laid out very simple things I see in data. If you go to the Q1 link, I have 2 simple questions. What would you do about the missing responses? And what would you do about contradictory responses? I'll be quiet and give everybody time to think a little. It's just an open-ended question. So if you want to type into that, whatever you think. So it's not like there's much to learn. It's just, you know, turn on your thinking cap. What would you like? What do you think is a reasonable thing to do at this point? Maybe that was also a very hard question. I'm not getting a lot of responses, or you're finding your, oh, okay. So yeah, people are needing to find their way to the survey. So I'm gonna now move this into the screen. I have one response. So one person said, if you have missing responses, yes, I showed you how you may do imputation, so maybe do that, right? And this person actually said, what would you do with contradictory information? It says reconciliation or discard. Yep. So, you know, if this is kind of one of those things, you only have a certain things you can do. You can decide to ignore the data because you can't figure out what's the right answer. I mean, reconciliation is a general approach. I'm not so sure what you would use to reconcile in this particular case, right? And then I have another person who said it imputes, but annotate that it was imputed so that you can backtrack if you need to. So, you know, imputed responses are not the same thing as the real response. So you want to be able to annotate it and make sure that you can do maybe another sensitivity analysis where you do it without the imputation and one with the imputation, right? This person said, if a relationship is stated once, impute for missing and annotate, right? Or there's somebody who's, okay, we have more fancy stuff like Monte Carlo. So randomly decide contradictions, run analysis on several randomly drawn iterations. So these are more simulation type of studies where you're gonna do this. Actually, I'm gonna talk about this maybe slightly differently, but I will talk about it, it's gonna come up. And then this person said, evaluate both the largest complete data set and total data set and analyze both. So it does feel like similar, like there is no good answer. You're gonna have to think about it, think about all the possible things you can do about it. Often this is do it in the different ways that's possible. And what that does is it starts to say, I don't know where the precise answer is, but maybe if I do it in all these different ways, I can kind of figure out the vicinity of the way where the answer is, right? So that's kind of what it is. Again, these are not things that I expected to have answers, right? But here is what they did do. So this group of people that did it the first time, in the social network analysis, the technical term is reconstruction. And what that means is that imputation, which means I don't care. So when you do reconstruction, actually, you are not considering the responses in red as a contradiction. You're just saying, you know, one person perceived it this way, the other person didn't perceive it this way. If you think of an organization and how many people are at the organization, does all my colleagues know all of my collaborators? No. So if this is really just one person in the organization answering the question. So if at least one person in one organization said, yes, I work with someone at the other organization, you might say that is a collaboration. It's probably a weaker collaboration than the most widely known collaboration, but you don't have to think of this as a contradiction. You could just say that is a collaboration, just a weak one. So in the reconstruction world, they don't think of this as a contradiction. They just say, what we will do is measure anything as an edge as long as there's any evidence whatsoever that there is a connection. So then then everything gets imputed so that, you know, this red becomes a 1, all the things down here get 1. So what they did, what the group that did this was use that reconstruction, which is a common accepted methodology in social network analysis, that said, anytime there's any evidence of a tie, just put it in. And that then all of the answers about missing and contradictions go away, right? So again, I'm just gonna ask you, so first thing I did, I replicated, figured out that that's what they did. And then I'm now pulling back and going, okay, do I wanna do that? Or are there any problems, right? So I'm just gonna, for now, leave it out there because of time. And then I'm gonna now go to question number 2 that I'm going with. So here I am, now I've figured that out. And I wanted to ask the question, I believe this is now gonna be question 2. Oh, actually question 2 is something a little different. So you're gonna go to question 2 and do this. So this is the raw Excel, literally the raw Excel sheet I was given. If you were me and you were trying to calculate the density of these networks, these 20 or 60, would you use the data in this format or would you change it is the question. And if you would change it, just try to describe how or why. So again, I'll give everybody a little time, but if you go to Q2, I have a few questions about reconstruction now that I explained what it is. And then, you know, the main question is, here's the raw data. Now we're really literally talking about, you know, doing wrangling. Does this look like it's in the shape that you need to do density, or do you need to reshape it is the question. And if you are gonna reshape it, how would you reshape it? Okay, so, you know, you're going to the Word document, finding Q2 and clicking on it. I guess I have a response now. I'm gonna check a little bit. Okay, one person has responded, reconstruction is, I don't know. Okay, there we go. Would you change the data format? And the answer is no. So this person thinks this data is in the shape that you need to do density calculations, right? Okay, we have another person coming in. This person said, yes, reconstruction is okay to do. And 100%. So both people who answered so far are saying, there's no wrangling to do. This looks like a perfect shape to do density calculations. Okay, maybe a few more responses. Okay, we're getting a few more. So let's see, 2 yeses, 1 no, or I don't know, 1 I don't know, 2 yeses. I have a yes, somebody does want to change the format. And it says retain original data set in all cases to go back. That is a good thing to do. So this is again, the data pipeline and provenance. It's actually, you should be very actively thinking about what are data sets I should keep, what versions should I save, what versions should I not keep, because it's getting confusing. There's going to be a million versions by the end of the project. So that's an active thinking you have to do and be conscious. This is a version, I want to make sure I save it because something could go wrong and I want to come back to it, right? So, you know, yes, save the original. So we have now 4 responses, still 1 I don't know, 5 responses. Okay, so we have 1 I don't know, 1 no, don't do reconstruction, that feels weird. 3 yeses. In terms of changing data formats, we have 2 people who said yes and 3 that said no. So I guess I will do, so again, none of the questions I have an answer. It's about the thinking that you're doing. So I'm gonna say, when I did this and I'm trying to calculate density out of this, yes, as a person, I can read something like this and I can calculate density. I don't expect to sit here and look through 60 sheets to calculate this manually. So my brain is going, okay, I would like to write a tidbit of software program that can calculate density so it can just spit out the 60 numbers very quickly. And when I think about writing that software, can I calculate density easily from this format data? For me anyway, the answer was no. So if you're curious what I did, I changed it to look like this. So it looks very different, right? I decided what I wanted to was pair everyone. So this is it's literally just combinatorics, right? For the simple 8 organization network, which I could fit on this screen, if I change my data like this, I can no longer fit it on this screen, right? You know, for all, the Webb County was the first, Webb County government agency was the first entity there. So, you know, Webb to all else, right? I did, you know, N-1. And then I just looked at the graph and filled in yes, yes, no's, right? I went to the second one, border region. And then I did this time, you know, so this is 7 rows because, so because I'm doing reconstruction, I don't need the full matrix. I only need the upper or lower because it's symmetric. So this is 7, this is 6, and 5, and so on, right? Because it's going to have equivalent information because I'm doing reconstruction, right? So I decided to turn it into this shape and then add a field called RHP. So this was RHP 15. Now I can take the 60 Excel sheets, that literally 60 of these things, and turn it into one table I can put into a program, right? So without going into details, this is why I thought it was worth changing it to this format, because I wanted to write one program. I want all my data into one table that I can actually do something with in a consistent way. So I looked at this. This is good for my thinking, viewing, figuring out what's going on. It's now time for me to go code. This wasn't working. So the first thing I did was I changed the format to be like this. So I read in the Excel sheet, I wrote code. So I wrote code that would take this data and turn it into this data. Then I added the RHP, and then I concatenated all of my things for all 60. So RHP as well as time T. So then you have the T0, T1, and T2. And now here I am with, I don't know if it's big data, but I've got now many rows, and I'm going to add even more rows because I'm collecting more data. This is much easier for me to now calculate the density as I need, right? I would write a few pivots of code and I would do that. So this is, I don't know, when you hear data wrangling, I know it's talked about a lot. I don't know what you're thinking. I know cleaning data, figuring out missing data, those are parts of it. But there is literally this, when you look at this and you're thinking, I need to calculate density, your brain should be thinking, stop thinking like a human being, think like you are a computer. How would I tell a computer? And this is actually how I talk about it. I consider a computer to be a 4-year-old. Very little vocab, knows how to do a few things well, pretty much nothing else, can't understand anything I say. And so you must be able to figure out how to tell a 4-year-old how to count things the way you want to count them. And you're limited to those few vocabs that they know how to do. So when I'm looking, I'm actually thinking, what is the shape of this table? So it's the easiest thing for me to command my computer to count density. And I don't quite know how to explain that, but when I looked at it, this is what came to mind when this was done. So usually this is also the case when I work with students. When I say, okay, go do density, they get lost and they don't know what to do. So they come to me. I'm looking at it thinking and go, okay, how about you go try taking the table like this? Then they go code it and then they go, I see, now I can calculate density really fast, right? So I don't know how you go from here to here and know to go from there to there. This is one of those arts part of, data science. The more you do this, the more you realize what shape of table, how many different tables, that you need so that you can calculate things so that your program is easy to maintain. I'll just leave it at that for now for the data shaping. So we did the Q2, and I'm going to now move on to this. So I talked about, so is this really big data? I don't know, but 80 providers. You turn this into actual counts of things. It is plenty big, and the main point here is to say, for me anyway, big data is in gigabytes, terabytes, petabytes. Big data is complexity in my data. And so for a data set like this, it gets pretty complex, right? And I'm already lost. So this has plenty of complexity for me to feel comfortable calling this big data. But here we are back again. So the blue are densities that was calculated from the precinct that I was given, that I replicated. Now I collected my new data, T3. So you have now the density calculated using the same lines of code. I got my density. So we're good here. So I'm going to now point to this part here. So because it's not that I need density. What I need is change in density, right? So here I am, I'm writing my report. I'm being told they would like to detect quantitatively the change in density from T2 to T3. That's 17% to 36%. If you will go now to Q3, in terms of your sheet, I'm just going to ask everybody, can you calculate what you think is the change in density between these two numbers? So if you go to Q3, it has one question. I would like everybody to pencil and paper or type it in. Calculate the change in density for these two numbers for me. Whatever you think is the right way to do it. And I just gave you an open-ended one, so you can, whatever way you would like to calculate the change in density from 17% to 36%, I would like everybody to type in their answer. in Q3. So this is TAMIDS Q3. Okay, so let's see if I can figure out how that'll work. Yeah. So far, no responses, I think, but I'll wait. And this isn't a trick question. This is pretty straightforward. I think people in this room could probably detect the change in density and calculate it. Really, no one. How about I give? Oh, okay. We're starting to get. Somebody said 19%. You know, subtract 36. Subtract the two numbers, you get 19%. Two responses. Yeah, I'm gonna give it a little more time. See if other people have other ideas. No one. So is this obvious to everybody how to calculate this? No? Okay, so here we go. Somebody came back with a, no, not really. You might want to look at not the points difference, but the change percentage-wise. So you can divide either by 36 or 17, depending on when the baseline is. So yes, actually that does cover the point I was trying to make. Even something like this, as simple as changing the detecting the change, it's not, so on the surface, it might look so simple, like what's there to discuss? Actually, I would beg to differ in that there is actually 3 different ways to do this. So here are the 3 different ways. You could say it's a point change. So here we go. This is what was in the, you can do a point change difference. You can actually do a percent change difference. But if you're going to do a percent change difference, you need to know what to divide by, right? So I think I have it here. Yeah. So here are the 3 different ways. 17, 36. So you can get 19% if you divide by A. See the difference? If you divide by A, it's 111%. If you divide by B, it's 52.5%, right? So what I'm trying to say is you have to think carefully to figure out, is it this one, this one, this one that's appropriate for what you're working on? A lot of data science, the devil's in the details. And I often see lots of people who are young who, it's not that they're lazy in thinking, it's that it never even occurs to them there's something to think about, or something like this, right? So it's you have to get used to it, because it really matters whether you're looking at point change or percent change. And if you're doing percent change, what you're dividing by, right? So it's, again, doesn't have a right answer, but those are things you should be thinking about. Those are things you should be talking to your clients about, to see what is it that they're trying to do, which is the one that they should think as a baseline. In this case, in this particular case, you can think of baseline, because, and I like the way this person answered the question. You can think of baseline because this has got a time period going on. So you just think prior is baseline. So then it's not very confusing. Lots of things when you're detecting change, it's actually unclear what is or what should be the baseline. So this is what I meant by, it's never the case your client's going to come and say, I'm going to tell you baseline is X. They just tell you, hey, tell me what changed. It's your job as a data scientist to do all these calculations and go, okay, at this very moment, I need to know which one's the baseline. I'm not the content expert. So now I need to go explain to my client, what is my data question? Like, I need to know what the baseline is. This is why I need to know what the baseline is. Can you go think and tell me what the baseline is? You have to be able to identify those situations, have those conversations so you can facilitate your clients telling you what it is that they're after, right? The other thing that this is a totally different point now. I'm moving on to the next point. So here we go. I said, you know, when you subtracted it, it says 0.19. That's the math. We all know that. On my sheet, it says 0.2. This is an Excel sheet, by the way. It says 0.2. I'm thinking most of you know the difference between why my thing says 0.2 when the answer is 0.19. That's an obvious one. It's precision. So it's going back to that quality or precision you need. So this Excel sheet has been formatted to only have 1 decimal point after the point. So it's 0.2, which means 0.19 was rounded up to 0.2. The thing that I wanted to actually bring up, and I'm not sure I have it on this slide, is to say, what I'm trying to say is, just keep in mind what you see is not what you get in computers, right? You see 0.2, you might even see 0.1 if you increase the precision, 0.19 I'm saying. What's actually stored on your computer is neither. So you, as a data scientist, I find this really important. Somewhere in your brain, you have to know what's stored on your computer, what's exactly stored on your computer is not the thing you're looking at. And those gaps in what's stored in your computer and what you're looking at can lead to confusions in thinking through things. So at the moment, with time limits, I'm going to stop there. But often you have to work up, you need to remember what you're seeing is not what's inside the computer, really. I'll just leave it at that. So I'm going to go, so now you think you're done. Like I'm actually almost close to time, so I have to be done. But I'm going to say, actually, anybody have any idea why it's not working still? I mean, you can chat in the chat box, but I haven't even started in a way. And anyone have, it's a, here you are, let's say you are me, you are here, and you think, okay, I'll go write my report. Well, I'm going to tell you that is not the answer. Anybody can guess why that's not the answer? There's a question to ask here that somebody ought to ask if you can see beyond the obvious. Okay, in the interest of time, I'm going to move on. That is because no one asked me if the network itself is changing over time. So that's the point here. I added, now this is what you had the other part. So this actually gives you how many providers at different time points. And I just circled one thing here. You can see that if I'm measuring between T2 and T3, my network just, in terms of the nodes in my network, went from 40 to 20, right? So this whole density simple calculation only holds if the number of providers in my RHP stayed stable, right? Did you think to ask? I mean, that's again, here's the reality. Do things stay stable in reality? No. So while all this is going on, some providers are closing out, some providers are getting added. So between the 5 years, 2015 and 2020, the number of providers changed. And in many cases, so almost nothing stayed the same. And in some cases, it halved. So I'm going to leave it as a question, another open-ended question. Are the density calculations we did still valid when your network has changed this much? And I guess for the point of this talk, would you have thought to ask this question? So here I am, I replicated the studies before, I did everything, and what I realized is in the prior study, they didn't care that the network changed, the number of providers changed. So they never asked the question, they just did the calculations and wrote the report. When I looked at it, I go, this calculation doesn't make any sense, especially because, so if these were fully answered, no missing data, then okay, I can think about it. But remember, not only did the number of providers change, so I'm going back to this one. Not only did the number of, like, think about this, you're comparing this to another network of 16 of these, and you have missing data people didn't answer. So what I'm trying to say is, if you say, when you say that, so let's go back to the basic definition of density. I think I had it there. The question here is all possible ties. So what is the all possible ties? Is this all possible ties of everyone who answered my question? So of the 8 people who could have answered my question, only 6 answered it. So is my denominator only 6, or am I doing all 8 when I do the density calculations? And then with the number of providers changing over the 2 time periods and different missingness across the 2. Wait, so at this point, I'm just going to say I'm more lost than I know what to do. Does that make sense for everybody? So all of this is kind of the thinking I do in my data projects. And honestly, this is what I'm working on now. And I don't have a good answer as to, and I looked at the literature. It's not like the social network literature has an answer, because my gut instinct is this is not a math problem. It's not like I can come up with fancy math that can detect the change in the reality of the network structure changing and different missingness of different people responding. When at the end of the day, all they wanted was for me to quantify change in density of network over 2 time periods. That seems so simple. But when I got into it and looked at all of these things and trying to deal with the realities of the network changing, it's unclear to me what is best. And so I'm going to end on this one where we say, these are the different ways in the literature that you can do this. The complete case approach is to say, we will just not worry about people who didn't respond. So then that's changing the 8 organizations to the 6 organizations that responded. And just again, keep in mind, the goal is the delta. So I have T0, 8 people, 6 responded. I have T2, 8 people, well, not 8 now. actually now that the denominator changed, I have now potentially 16 and 10 of them responded. And so if I calculate the density using just the complete case, is that really reflecting reality change in density or amount of collaborations? Honestly, I don't know. The mean imputation is one where, okay, there's no other choice. So what you can do is you can calculate a mean for the network of the data that you have, and then everyone that hasn't responded, in order to have full data, you can put that in. Is that okay to do? I don't know, because the person who didn't respond most certainly didn't think that they were the mean, right, in terms of collaboration. Reconstruction I talked about. Again, the best methodology from a data method side is one I grayed out. It's called complex multiple imputation. That is one where, you know, like the MC one, this is what I was talking about. If you have plenty of data, you can kind of, instead of using one mean to impute every missing, you can kind of find a distribution of this RHP, network collaboration, and then you would randomly sample from the distribution so that the imputed values are not just one constant mean, but coming from a distribution. That is only possible if the nature of the data would allow this. This data does not allow this at all. So that's not something that we can do. So again, you know, from a data methodology perspective, you want to do that. Well, that's not one of your options. So then you're stuck with, at least in my case, I don't like any of my options, and I'm not quite sure what I want to do. So, you know, simple question, trying to do this. So here's how I did it, right? The issues are number of nodes change over time. I have incomplete data, and I don't have sufficient data this is the part about this, the nature of the problem is such that I don't have sufficient data that I can do simulations, right? And if you wanted to, the Q4 was, I was gonna ask people in this group who is comfortable with doing mean imputation, or I'm actually having an even more difficult time saying it is okay to compare two networks with different number of nodes. And the last, because I'm at the end, the last thing is, you know, I don't know if this comes to your mind, I often always have the other answer, which is, I could say, so to the people that came to me and said, can you detect change in the network collaboration? I could decide, I could say, I could do mean imputation. It has pros and cons. Should I do that? I could say, I can do what they did before, which was just to ignore the fact that the network changed and just compare. Somehow that's not acceptable to me. I would probably have a meeting with my client to try to explain the difference of these methodologies and see if I can have them make the decision. It's unclear to me that they will or can. And on top of that, I'm going to say, one thing that is always in my, when I ask these questions is it's not possible, I can't do it quantitatively. I think many of our data scientists and quantitative people, we forget not everything can be done quantitatively, even if we so desire to do it. So honestly, when I'm working on this, I work with qualitative researchers as well. And the people who are the content experts, people who know healthcare, they kind of looked at all of this, and I explained all the ways we can do this. They're more like, you know what, this was a lot of work to try to quantify something that would have been good to quantify, to learn maybe the simple qualitative, tell us about your collaboration between these two time periods, and going the qualitative right. It wouldn't be a number that you can pick, but may give you more information than trying to go about this in a quantitative way. I don't know what the right answer is, but I wanted to leave with saying, I have identified these data issues and then clearly laid out what the issues were and what are potential steps, or what are potential options. You now are at the point where either you're making the decision, you're looking for experts who can help you make a better decision, or you're going back to your client to say, this is one that doesn't have an answer, but which one would you like me to try? Is this a sensitivity analysis? And in all of that conversation, you should always remember that not everything is possible to do quantitatively, even though it feels so simple. I think that would be a good place to end this talk.